All right, so for this last video, I want you to kind of remember what we talked about in the phase change videos. That when we looked at the phase change diagram, the main point to remember and how to categorize that diagram is that there are always one of two things going on. Either temperature is changing or the phase is changing. Remember, you can't do both at the same time. So we're going to have two separate sections for this. The page for temperature change and phase change is divided into two sections purposefully for that reason. And so we're going to start with temperature change. There's an equation for temperature change. It goes in the box. The equation is Q equals mc delta T. That's an equation in the chart. You don't have to memorize that, just like all the rest of the equations that we have. Because we are out of mechanics, a lot of these variables are going to be new to you. So let's talk about what they mean. First of all, the Q means heat energy or thermal energy. And to do a temperature change, that energy either has to be added to an object or a substance or removed from an object or a substance. Heat energy, as with all other energies, is measured in joules. Joules is the unit. So this is the energy that is added or removed. Q equals mc delta T. M is mass in kilograms. We've had that before. And then C. Make sure when you write this, this C is lowercase. The lowercase c stands for specific heat. And I know that can be difficult to remember, but just remember specific heat. And right now, the most important thing you need to remember is writing down the unit for it. Joules per kilogram Kelvin is the unit for specific heat. In just a minute, I'll talk about what that means. And then you might realize delta T, make sure you wrote T as a capital, not lowercase. Delta T is change in temperature. And the unit for that could be Celsius or Kelvin. It doesn't really matter, because remember that those two, the scales are the same. So for instance, if I take water from freezing to boiling in Celsius, that's a 100-degree temperature change. And it's the same for Kelvin. Kelvin is from 273 to 373 freezing to boiling. And it's also a 100-degree temperature change. So it doesn't matter whether you have your temperatures in Celsius or Kelvin. You subtract the two, you can get the temperature change. Make this note to yourself. Make sure that delta T, when we calculate this, when we use this equation, delta T always needs to be positive. The reason for that is thermal energy, Q, always needs to be positive. All energy is positive. Energy cannot be negative. And what's going to happen is it's going to be a positive amount of energy that is either going to be added to or removed from an object. So the only way to get a positive Q is to make sure delta T is positive. So you might even want to, you could put in absolute value marks for this delta T just to make sure you remember that it needs to be a positive number. Before I go on to talking about what specific heat is, I just want you to kind of notice that the amount of Q, the amount of heat energy that's required to raise or lower, let's just say raise for right now, required to raise the temperature of an object is dependent on three things. And it's these three things that are in the equation. Right? So the amount of temperature, or the amount of heat, first of all, that's required to raise the temperature is determined by mass. So that means that the more mass you have, the greater the mass of the substance you have that you're trying to change its temperature, the greater heat that takes. So if you have 10 kilograms of water and 1 kilogram of water, it's going to take more Q, more heat energy, to raise the temperature of that 10 kilograms of water. If you're going to cook a mug, you're going to heat up a mug of water in the microwave versus an entire bowl of water, the mug is going to happen faster because it's smaller mass. So number one, it depends on the mass. Number two, the amount of heat it takes to change something's temperature is dependent on the specific heat. And we'll talk about what specific heat is in a minute. But basically, each kind of substance, each different substance has a different amount of specific heat, which means it takes a different amount of heat to heat up. So that's the second thing it depends on. And the third thing is pretty obvious. It depends on the specific temperature change we're trying to achieve. So obviously going from 10 degrees to 20 degrees Celsius takes less heat than going from 10 to 50. It's a greater temperature change, which requires more heat. All right, so those three things are what determine the amount of heat energy required to change the temperature. All right, so now let's talk about specific heat. Read this definition before you write it down. Specific heat is, specifically, pun intended, the heat required to raise the temperature of 1 kilogram of a substance 1 degree Celsius or Kelvin. You can pause the video and write that down right now. So it's called specific heat because, number one, we're talking about a very specific set of circumstances. We are talking about 1 kilogram of a substance, whatever we're talking about, any substance, water, gold, aluminum, whatever it is, we're dealing with 1 kilogram, and I want to raise its temperature by 1 degree specifically. So that's a specific set of circumstances, and it's also called specific heat because it's specific to each individual substance, specific to each individual substance. So if you look at this table right here, these are tables of specific heats, and this number represents the amount of heat required to raise the temperature of 1 kilogram of that substance by 1 degree Celsius. So if I have 1 kilogram of each of these substances, it takes a different amount of heat to change their heat. So which substance is going to heat up the fastest? What do you think? Pause the video and see what you think. Well, the answer to that question is gold. Gold heats up the fastest, and the reason is because in order to heat up 1 kilogram of gold, it only takes 126 joules of energy to raise its temperature 1 degree. If I'm going to raise it 2 degrees, I got to multiply that number by 2. Going to raise it 3 degrees, but I got to multiply that by 3. Which substance will heat up the slowest? Well, that's water. The same amount of water. We have the same amount, 1 kilogram, going to undergo the same temperature change, 1 degree Celsius. It takes 4,186 joules of energy. That's obviously a lot more energy than the 126 joules that we saw here. And ethanol and aluminum are going to be in between those two. So each specific substance, every type of substance, requires, based on a lot of properties of their chemistry, a lot of molecular properties, density, a lot of different things, they require a different amount of heat to heat up, and when they cool down, they're going to release a different amount of heat. We're going to talk about practically what that means in a minute. Third question, if I heat the same amount of all 4 by 10 degrees, so let's say I have 1 kilogram of all 4 of these substances, and I heat it by 10 degrees. Now, which one will end up with the smallest amount of Q? Remember, Q is heat energy. Which one ends up with the smallest amount of Q? Well, if I go up by 10 degrees, that means I'm going to multiply this number by 10, because this is for a 1 degree change. For a 10 degree change, this times 10 is 126. This times 10 is 41,860. That's how much energy you have to deposit into that material to raise its temperature. Therefore, which one ends up with the smallest amount of heat? Well, it's gold. Gold will only end up with 1,260 joules of heat to raise its temperature by 1 degree, versus water will end up with 4,186 joules, or 41,860 joules. Ethanol ends up with 24,410 degrees or joules of heat, and aluminum ends up with 9,000 joules of heat. Okay, so in the middle of the page you see that flow chart, and that flow chart looks something like this. This is basically here to help you understand practically what specific heat really means. First of all, high C is not the drink. That means high. Remember, C is the letter we use for specific heat. So this is high specific heat. This is low specific heat. And you need to know a substance that has notoriously high specific heat and one with low specific heat. And you saw on the previous slide, water has the highest specific heat, at least on that page. And water has a notoriously high specific heat of all materials. It's not the highest, but it has a very, very high specific heat. A low specific heat, on that table it was gold. I don't want to use that as an example here because not a lot of us deal with gold on a daily basis. But air, a lot of us deal with air on a daily basis. So you need to know that air has a notoriously very low specific heat. Well, here's what that means. In order to explain that, let's think about this. Imagine if you have a pool. All right. So if you have a swimming pool, around April is going to be, at least here in Texas, it's going to be our first 90-degree day, 90 degrees Fahrenheit, about 33, 34 degrees Celsius. It's a warm day. It's not exactly comfortable to be outside. You might be tempted to go and jump in your pool then. But if you did, you would find that your pool is very, very cold. And the reason is because it's been in the cold temperatures all winter long, and it's too cold. It's very cold from the winter. Even though the air is 90 degrees, it takes longer for your pool to warm up to the point where it's comfortable to jump into. It's going to be like, I don't know, 35 to 40 degrees Fahrenheit to jump into. It's very cold. It takes about May, June-ish for your pool to get comfortable to jump into, to where it's warm outside, but your pool is cool enough to feel refreshing and relaxing. It cools you off. But then as the summer wears on, your pool still continues to heat up as the daytime sun warms it. And if you don't replace the water with cooler water, now it's, say, August 4th. August 4th, it's 95, 100 degrees outside. It's not going to be very refreshing to jump into your pool, because at that point in time, the pool has warmed up and it's about 92, 93, 94 degrees in the pool. It's a warm water environment. It is warmed up. And then fast forward a little bit more. Now it's October, November. We get our first real good cold front, and it's like 40, 50 degrees. Feels nice and cool outside. And at that point, if you're cold, the most interesting way to go and warm up is to jump into the pool, because the pool is still warm from the summertime. It's still warm. It still retains that heat, because anything with water has a high specific heat. That means it heats and cools very slowly, a lot like this tropical rainforest. The temperature in a tropical rainforest, which, by the way, in case you don't realize, the most important feature of a tropical rainforest is water. Lots of it. Lots of rain, lots of water, almost 100% humidity all the time. And it does the same thing as your pool does. It heats and cools very slowly. The sun goes down at night, and the temperature will decrease a little bit, but not very much, because that water has a lot of heat energy bound up in it, and it takes a long time to release it, just like your swimming pool. And then when the sun comes out in the daytime, the temperature will rise, but it doesn't rise very much, because the water in the air requires quite a lot of energy to warm up. So water heats and cools very slowly. The reason it heats and cools very slowly is because it requires more energy to heat up, and when it cools down, it's got to release more energy, because that amount of energy was put into it to heat up. Think also about water. When you boil water on a stove, it takes a long time to do that. Have you ever heard the phrase, "a watched pot never boils"? That's basically saying it takes a long time for water to boil. So water has a high specific heat, and anything with high specific heat, not only water, heats and cools very slowly. And the reason is because the high specific heat means it requires more energy to heat up, and it has to release all of that energy, a lot more energy, to cool down. But then let's think about low specific heat. Let's think about air. And for example, on this one, I want you to think about a desert. The most important feature of a desert, as opposed to a tropical rainforest, is that there is little or no water. Not in the air, not in the ground. There's no bodies of water. And so the air itself doesn't have saturated water. There are no water molecules, or very few water molecules in the air. Air itself has a low specific heat, which means it heats and cools very rapidly. And if you've ever been to a desert, let's say Phoenix, Arizona, you might have noticed that it does get very hot, but it isn't hot all the time. The temperature rises very rapidly in the morning, and it gets very warm during the daytime. But at night, it cools very quickly. It cools off very rapidly. The reason it cools very rapidly is because there was not a lot of energy that was deposited into the air to heat it up. It has a low specific heat. Therefore, to release that energy, it has to release a lot less energy than the water did. So the result is, with an arid environment, we have large temperature swings. In the most arid deserts in the world, say take the Sahara Desert in Africa, for instance, it's not uncommon during the daytime to have temperatures in excess of 120 or 30 degrees Fahrenheit even. We're talking about 40, 45, 50 degrees almost Celsius. But in the same 24-hour period, when the sun goes down, you better find someplace warm, because it will cool down rapidly, and at some point during the night, in the same 24-hour period, you might find ice crystals on a cactus. And the reason is because the air cools down very rapidly. up to 100-degree temperature swings in a desert simply because of low specific heat.